Okay, good morning. We will just, okay, just complete the discussion associated with transition rates and also look at some consequences of the form of the matrix element, the dipole matrix element. Let me just write down, okay, the transition rate that we should have obtained last time. I don't know if I missed any factors or anything, but this is the correct form. Pi over epsilon 0 h bar squared, and then there's this magnitude of p squared rho omega 0. Okay, so we have the energy density associated with the electric field. That's where the epsilon 0 comes from. And so the transition rate from A to B, remember what A and B are. These are two energy states, okay, EA, EB, with an energy difference of h bar omega 0. Okay, and so we found this is the transition rate per unit time to go from one state to the other. Now, we just looked at this as a two-state sort of event, but now if you want to apply this to a really more practical type of problem, let's see where that P came from. Okay, so for P, we took the expectation value between B and A of E, the magnitude of the electric field, times the Z coordinate. Okay, so this is the form that we used. Why did we use this? Okay, so let's go one step back. We had this H prime, which we said is going to have the form E0 times Z cosine omega t. Okay, so that was the time dependence associated with the potential. Now, there's a slight problem with this. Okay, first of all, let's see why we have such a potential. Well, we have some object, some atom, whatever, which is quite small, we assume, and is under the effect of an electromagnetic field, which is moving in some direction. Okay, and we said, okay, let's choose the electric field. Okay, so this is the electric field, and it's going to be in the Z direction. So this is as some other direction. Okay, so this is, say, I don't know, X or something. And this is the Z component of the electric field. And this electromagnetic wave is moving towards the right. Now, you see, if you just look at this thing carefully, not all parts of the atom see the same electric field. But what we assumed is that the size of this atom, okay, whatever it is, okay, some hydrogen atom or something of that sort, the size of the atom is of the order of angstroms, while the wavelength associated with these transitions are micrometers or fractions of micrometers. So there's something like 10 to the 3, 10 to the 4 factor between these things. So I can assume that it's a good assumption to assume that the field on the atom is uniform at any time. But we'll see that we can make a correction even for that, okay? But that will come later. Now, okay, so this is the form that we used, and then we are using, if you want to use the atomic states for these things, okay, then remember the atomic states that we solved them in a spherical coordinate system, but the spherical coordinate system, okay, doesn't have to align with the electromagnetic field, right? So this hydrogen atom, we solved it in spherical coordinates, and we said, okay, so there are these NLM objects, but the angular momentum states are in terms of L squared and LZ. Okay, so that LZ doesn't have to correspond with the direction of the electric field. Okay, so these are two, okay, independent directions. So we have to be more careful here. So this was okay for this two-state object, but now we have to actually look at this. So what we are going to do is we are going to use a somewhat okay, modified H prime. So H prime we'll use something which looks like E, okay, magnitude E0 again, but it may be, okay, the polarization of the electric field may be in any direction. Okay, it doesn't have to be X, Y, Z. So in fact, we are effectively, what the problem that we are discussing is we are going to put this object, the atom, in a box, okay, or some surrounding in which we have this energy density, okay, rho omega 0. And inside this box, I have this atom, okay, aligned in some arbitrary position, okay, so there will be many of these atoms, two-level atoms, and their Z is going to be in one direction. Okay, the polarization of the electromagnetic field that's hitting it is going to be in some other direction. Okay, so we are, instead of using the Z coordinate, we are going to use the general R coordinate in place of Z. And then at this stage, we are just again going to assume that there's this simple cosine omega t variation. Okay. So our P now becomes this quantity where I have, okay, these states which are now hydrogenic states, NLMs, maybe I should put that down explicitly, N prime, L prime, M prime, and the transition is between these E, okay, I'm not going to include, I'm sorry, E0 is not included here, right? So that's just my polarization vector. E0 now is hidden inside rho omega, okay? All right, so now I have this E and then N dot R, okay? So that's what I have, N, L, M. So for in an electromagnetic wave with a certain definite polarization, and R can be the position of the electron in this XYZ coordinate system, and that's what I'm going to consider as the matrix element between the final state and the initial state. Okay, so it will end up in our transition rate equation as R from A to B, okay, is equal to pi over epsilon 0 h bar squared. So rho omega 0, that is the same, but now I'm going to get something which looks like the magnitude of this thing, okay, so N prime, L prime, M prime, and then I have E N dot R, okay, NLM, okay, but this is not very useful, right? For this to work out, I have to know the orientation of the atomic orbitals and the electromagnetic field that's hitting it, while actually they are really quite random, okay? So the atom may be oriented in any position, and the electromagnetic wave may be coming from any direction. So I should somehow average this over, okay, over the direction, okay, the relative direction of these things. Okay, so what I can do is, let me write one more line. So it's going to be pi epsilon 0 h bar squared rho omega 0. If I just evaluate this dot product, what do I get? I get, okay, n prime, l prime, m prime. Then I have here an e times r, and then an l m, okay, and the okay, so this is, what am I doing? Okay, so this is the unit vector in the direction of polarization of the electric field. R is the direction of the position of the electron, and there's a cosine theta factor here. Okay, so the averaging over n is really going to be an average of cosine theta squared. Okay, so average over all directions that n can be coming from. Okay, so what do we have? Again, we have two directions. One of them is the direction n for the direction of the electromagnetic wave. So let me assume that the atom is here someplace, and electromagnetic waves can be coming in from any direction. Okay, so that the polarization vector can point in any direction. Okay, so that's our n. And then I have this angle theta. Let me choose the z-axis, okay, to be the direction in which I solve the Schrödinger equation. That's the direction I choose, so that I get these eigenvalues in the z direction, okay, these NLMs. So there's an arbitrary angle between n and z, and obviously it involves two angles. Okay, so the direction of n relative to my NLMs are going to be random. Okay, but the averaging is just, okay, so the factor it brings in is just this cosine squared theta, and if I just average this cosine squared theta, it's just going to be 1 over 4 pi. Okay, so I'm averaging cosine squared theta over all angles. So I'm going to get this sine theta, d theta, d phi factor integrated over all angles. So there's no phi dependence. The phi integral just gives me 2 pi. And this is our favorite integral. We write this piece as dx, this piece as x squared, and integrate from -1 to 1. Okay, so the integral part, so let me write this out in full, 1 over 4 pi. This integral is going to give me 2 times 1 over 3, and then there's also a 2 pi factor. Okay, so 1 over 2, so this just gives me 1 over 3. Okay, so this is 1 over 3. All right, so what do we do? Okay, so let me just write this down someplace where I won't lose it. because I'll need it again. Well, we can always write it again. So the end result is that R A to B is just including this averaging factor, pi over 3 epsilon 0 h bar squared rho of omega 0 times the n prime, l prime, m prime. Okay, this is okay. I have to write this as ER, but okay, let me write this P and L M magnitude squared. So it's the magnitude of R anyway. In any case, you see we no longer are restricted to the z direction, because z direction is not special. This transition rate now includes everything, okay? The x direction, y direction as well. So that's because the electromagnetic wave may be coming from any direction. So the effect that has is just to introduce this factor 1 over 3, okay? All right, now having said that, if we want to look at transitions, we have to calculate this object, and that object is in the form, okay, so this P is in the form of E times, okay, x times x plus y times y plus z times z, okay, E times R. So the expectation value here is going to involve average values of x, or matrix elements of x, between two states of the system. Okay, so we are going to need, okay, objects which look like, okay, so we'll need things which look like average value of n prime, l prime, m prime, say x or y or z between the initial and final states, so that we can put it in there. Okay, so there is a nice way of eliminating certain set of those things due to symmetry. Okay, so these selection rules are rules which enable us to select which one of those matrix elements are going to be finite or not finite. Okay, and these things involve a trick in which we look at commutators of these xyz with the lz. Okay, so consider the commutator say lz with x. Okay, what will I get? Okay, well, I have to do the commutation relation. So lz is x py minus y px. So lz with x is going to be this thing, x py minus y px, commutator with x. So the only thing that doesn't commute here, okay, because I have x on the right hand side, x will commute with y and py. It will certainly commute with itself, but it will not commute with px, right? So this is going to give me minus y px x. Okay, so this just gives I h bar, but it's in the wrong order. So it's involves a minus sign, so it's going to be I h bar y. Okay, so that's the commutator of LZ with X. Let's look at LZ with Y. Okay, so again, X Py minus Y Px with Y. So now the things that do not commute are Py and Y. Okay, so it's going to give me X Py Y. Again, it's minus I H bar, but there is no minus sign to save us this time, so it's my minus I H bar X. Finally, what is LZ with Z? Okay, 0, because there are no PYs in LZ, so this is just going to give me 0. Okay, so how are we going to use these? Okay, so what we do is we look at this matrix element. Okay, so we look at n prime, L prime, M prime, and let's put the commutator in LZ with X, N, L, M. Well, we just calculated what this is, so I can write this as n prime, L prime, M prime. LZ with X was I H bar Y. Then it's stuck with Z, that's easy. Okay, because it's just 0, right? So let's see what we get, and then we move on to the others. Okay, so that's that. But now let me write the left-hand side. So this is going to be n prime, L prime, M prime. And then I have LZ Z minus Z LZ and LM. Okay, so this has to be equal to 0. So you see these are eigenstates of LZ. So I can operate toward the left there and toward the right over there. So when I do that, on the left-hand side, I'm going to get H bar M prime, about the same thing. So Z is still there. On the right-hand side, I get minus H bar M. Okay, and N prime, L prime, M prime, Z, N, L, M equals 0. Okay, and that means I have this. Okay, I can just remove the H bars. Okay, cancel the H bars. So what does this say? This says this has to be, this is 0. Okay, and that means if M is not equal to M prime, this has to be 0, right? If M is equal to M prime, then again this could be 0, but certainly for this thing to be non-zero, M must be equal to M prime, okay? So this implies that the change in M, okay, so M equals M prime, okay, or another way of saying is that delta M is equal to 0, okay, if N prime, L prime, M prime, Z, N, L, M is not equal to 0. Okay, so this tells us, okay, this is something that we could have guessed, right? Because remember the form of this expectation value I have on the left-hand side, so this looks like R N prime L prime complex conjugate R N L N and L R. Okay, so that's the radial part. But then there is the angular part, which is going to be L prime M prime complex conjugate and Y L M, right? And the expectation value is that of z, which is r cosine theta. So I'm not going to have any phi integral, so now I integrate this over all the angles. You see, because of the orthogonality of these YLMs, I must have, okay, so this is going to give me m prime. Okay, if m is not equal to m prime, there is no other phi dependence in the problem. It's going to give me 0. Okay, so that's not unexpected. You are going to get the, you need to have m equal to m prime. But I cannot go through the same argument if I have an x here, for example, because x is going to have a cosine phi here, right? That's going to have a that's going to be sine theta cosine phi. Okay, so let's see what happens for the other cases. All right. So let me just put this in a box. So that's one result. Let's see what happens with the other commutators. I have n prime, l prime, m prime. Okay, and then I have let's see, let's put LZ X, okay, and then NLM. So we figured out that this is going to N L prime M prime, and I have I H bar Y N L M. But the left hand side is going to be, again, I just use the same trick, N prime M prime L Z X minus X L Z, okay, N L M. Okay, the right hand side just becomes I H bar. Okay, let me use a shorter notation here. Okay, let me call this piece here the B state, and this one here the A state, so that I don't have to write these NLMs all over the place. Okay, so again, this operates towards the left, and this operates towards the right. So what do I get? I get M prime minus M H bar, expectation value of B X A, okay, is equal to I H bar B Y A. So, okay, I cancel H bars. So that's nice. This just says that if you know, for example, the expectation value for X, you can get what the expectation value for Y is, okay? So it says that they are just related. Let's look at the other commutation relation also. So I'm going to get this N prime, L prime, M prime, L, Z, Y. So you can guess what happens. This is going to be N prime, L prime, M prime. And now I have minus I H bar X, okay, N, L, M. Okay, and then this just tells me, again, let me just do it quickly now that we are doing this for the third time. Let me just put in these things. So it's going to be H bar M prime minus M, just like the X equation, yes?
In the equation that you wrote with M prime minus M,
yeah.
Isn't every part except I is real, so how does that equality?
No, these things can be imaginary, right? Because this is not a diagonal matrix element. Okay, so I have BA, right? So in fact, these things contain things like e to the I Phys, which make them complex. So when you have okay, things like cosine phi and such things, in general, it can bring in imaginary factors. But since it's an Hermitian operator, obviously, AB is going to be the complex conjugate of BA. Okay, so this time we have BYA is equal to minus I H bar BXA. So same sort of thing. If you know this Y, you can know that. But now we can combine these things. Okay, so I can take this term here and put it in there. Okay, so what happens? I have to divide by I, so that means I have to multiply by minus I, right? So what I'm going to do is I'm going to combine these two objects. And what do I get? Okay, so H bars have cancelled. And I'm going to put this, okay, so this is going to be M prime minus M. Okay, BYA, which is going to be minus I times M prime minus M. Okay, BXA is equal to, okay, let's see, minus I BXA. Okay, so minus i's cancel. And what do I get? I get M prime minus M squared, okay, BXA is equal to BXA. So what does that mean? That means if this is to be finite, okay, M prime minus M must be equal to plus or minus 1. Okay, so I need to have M prime minus M equal to plus or minus 1, or, okay, delta M equal to plus or minus 1, okay, if this BXA, and also since they're just proportional to one another, BYA, are not 0. Okay, so you see, if we are looking only in the z direction, we could have missed these things. But this says that I can have transitions, okay, between two states. So this limits the matrix elements associated with the transition. So if I have a transition, it must either conserve the z component of the angular momentum, or it can change it by 1 h bar. Okay, this is really related to the fact that the photon has 1 h bar angular momentum. So when it's absorbed or released, okay, conservation of angular momentum says your atom should, okay, go up or down by 1 h bar of angular momentum. Yes?
Polarization direction is not like specified and it can be random. Why can't we have the transfer of angular momentum in the quantization axis?
In which axis?
Z-axis. In the z-axis, we don't have.
It is okay. Delta m changing by plus or minus 1 means the angular momentum in the z direction is changing by 1, right? Because m corresponds to the angular momentum in the z direction. Okay? Because we solved the problem in the z direction. But of course now the polarization of the electromagnetic wave is uncontrolled, so it could be making other changes, etc. But our solution, our quantum mechanical solution, does not allow us to follow the angular momentum in other directions. We can only follow the total angular momentum and the angular momentum in the z direction, in one of these directions.
So if we have our polarization pointing at the z direction, then we can't have.
Yes. Okay. All right. So we have those two rules, which are very nice. Okay. Let me. I have to schedule my time accordingly to discuss what we are going to do next. Okay, there are another set of angular momenta selection rules. So let me go on with that. Let's see. We are going to get. Okay, I am trying to decide what not to erase. All right. So maybe I'll do it over here. Okay, so the next set of selection rules involves, okay, so this is a selection rule, the one that we just discussed was a selection rule for M. Now, I want to find a selection rule not with respect to the z component of the angular momentum, but total angular momentum. Okay, so I want something which involves not m's like this, but L. Okay, so if I want to use L's, what type of commutation relations would I need? Which operator would be nice in place of LZ? Well, we have not included spin in here at all. So not the total angular momentum, but the angular momentum associated with L is L squared, right? Okay, this is just the L squared. So you want something which involves L squared and Z. Okay, so I'm trying to decide on my timing. Okay, let's start and see where we get. I'll at some point just write down the answer. Okay, so we now need something which involves L squared with Z. Okay, so that I can put that into, if I find the expectation value of that, or find the matrix element of that and relate matrix element of Z to things with L squared. Now, to do that, I have to really look at what is, so this is equal to Lx squared plus Ly squared plus Lz squared with Z. Okay, so I have worked out how these things commute with LZ and such, but I now need to look at the commutation relation of z with Lx squared, Ly squared, Lz squared. Okay, so I know how the commutation relation between Lz squared and Lz, at times are just Lz and z, but I'll also need Lx and Ly. Okay, so what I have over there was just a list of expressions that were related to Lz with x. Now I need the same thing for Ly and Lx, so I don't want to go through the whole algebra, but I know that since space is isotropic, if I just make a rotation so that z goes to x, x goes to y, and y goes to z, those relations should work again anyway, right? So let me just make a table here of these things. Lz with x was equal to I h bar Ly. So what's the best way of doing this? Okay, and then I'm going to have here Lz with y. Y, thank you. And Lz with y is minus I h bar x, and Lz with itself, Lz with z is just 0. Okay, so I have these three relations. So what I can do is I can just make z and x, x into y and y into z, and these things should work. Okay, because it's just choice of the coordinate system. So that's very nice. This just says Lx with x is 0 and Ly with y is 0. Over here, Lx with y is I h bar z, and y with z is I h bar x. Similarly, okay, Lx with z is minus I h bar y, and Ly with x is I h bar z. Okay, so these are my relations which I'll use. Okay, so Lz squared with z, okay, that's the simplest one. It just gives you 0, right? Because Lz commutes with z, so it will commute with Lz squared also. Okay, so now I am going to need, okay, things like Lx squared z is equal to, let's just expand this, Lx squared z minus z Lx squared. So what I'm going to do is I'm going to walk this z 2 steps to the left using the commutator, and then cancel the original term. So I'm going to get Lx, and in place of Lx Lz, I'm going to put z Lx, but I have to add to it the commutator of Lx with z. Okay, and then I still have my z Lx squared. So Lx with z is, it's difficult to find this, okay, I h bar y. Okay, I h bar y. So this is going to be equal to okay, Lx z Lx plus I h bar Lx y. Okay, I have to be careful with the order because these things do not commute. Minus z Lx squared. And then I'll walk this one more time. So it's going to be z Lx plus commutator of Lx with z. Okay, multiplied by Lx on the right hand side, plus I h bar Lxy minus z Lx squared. But now z Lx squared and z Lx squared cancel. So I take those terms away. And Lx with z was I h bar y. So I end up with something which looks like I h bar y Lx plus Lx y. Okay, so it's not commutator, but it's just adding these things together. And that's it. What I'm going to do is I'm going to use the commutator again, okay, so that I am going to get the two of them in the same order. So I h bar y Lx plus, okay, instead of Lxy, I'm going to put y Lx again, but I have to put then Lx with y, right? And Lx with y is I h bar z. Okay, so I end up with 2I h bar, and I have y Lx, and then I have an minus, okay, I don't like the minus, Lx y. Okay, I have removed all the minuses from my table, but okay, so these things are minus. Did I use any of them? Lx with z, yes, I used Lx with z, which is not good. Okay, so Lx with z was minus I h bar, so where did I use that? So this should really be minus. Okay, sorry about that. So that's going to be minus, and this is going to be minus, that's going to be minus, which means I'm going to get minus I h bar, so this is going to be minus, and this is going to be minus, so I get the plus h bar squared z, which I like. Okay, so how are we doing on time? All right, what I am going to do is I am just going to write down, okay, let's see, I'm going to, you see this is some considerable algebra. So I'm going to tell you what Ly squared z is. You can sort of guess that it's going to be very similar to this. It's going to be plus 2I h bar and x Ly plus h bar squared z again. Okay, so the z part doesn't change, but these things do change. So, and I know that L squared z is 0, so that means I can just add these things up, and I get L squared z is equal to 2I h bar x Ly minus y Lx. You see this starts to look like a cross product, plus 2 h bar squared z. So each one of these, so it's just the sum of these two terms. All right, so you see I get something like this, but it's not very useful. So the useful form is, believe it or not, L squared commutator with L squared z. So now you have to take this, okay, and look at its commutator with L squared. It's not really so bad because Ly and Lx commute with L squared, right? And so the only things that do not commute are things like x, y, and z, which we have over here, but still it's quite a bit of algebra. So I'll just write down what it is. It turns out to be 2h bar squared z times L squared plus L squared times z. And what's nice about it is that L squared is spherically symmetric. It doesn't care whether you put here a z or an x or a y, okay, it will behave in the same way, okay? So in some sense what I'm saying is that if you make this transformation, z going to x into y into z, L squared stays L squared, okay? But z becomes x and so on. So a shorthand way of writing all of those equations is that L squared with a vector r, which is going to have components x, y, and z, is going to have to be equal to 2h bar squared r L squared plus L squared r. So whatever result we find for the z component, it will work for the x component and the y component, which makes sense because L squared is spherically symmetric. Okay, let's have our break and then we'll continue.